You guys, page 797, we're in the next activity. It's activity 3 out of our lesson, talking about compound probabilities, compound events, and the word and. We want to study what it means to maybe be dependent, but let's get into the conversation around socks. You have 2 red, 1 blue, and 3, we should say the word pairs, right? This seems kind of weird if you just have single colors, of green socks in a drawer. Suppose you reach into the drawer and without looking, choose a pair of socks and replace it, and then choose another sock. Oh, maybe it's not pairs. Maybe we want to see if you can get matching or just wacky day at high school, all right? And then choose another sock. You choose a total of 2. So in the selection process, you're not really looking at what's being drawn. You're just allowing the probability to control your outcomes. Use this information to answer each question. Does the action choosing the first sock affect the outcome of choosing the second sock? And literally, because of the word replace, the outcome of choosing the first sock does not influence the outcome of the second. Okay. Well, I haven't used a tree diagram very much, and so I wanted to set up here. I could use an organized list. That's on page 792. For this one, we're going to use a tree diagram to represent the sample space. And remember, sample space is all of the possible arrangement of the items. But sometimes having it in a visual, a little flow to it, is better than seeing it written out like in list form. So here's your first choice. This is you, and you're reaching into the drawer, and maybe you reach in the drawer and you get a green sock. What are the outcomes then? Because you're going to put that green sock back in the drawer. What are your outcomes for choosing, again, you're going to go back into the drawer and choose those socks again. So you could draw a red, you could draw a blue, and you could draw a green. Okay, that's just one scenario with 3 separate different scenarios for your second set of options. You know what? Maybe I said wrong. I said, I'm missing something. I'm actually missing 2 red, 1 blue, and 3 green. So I'm going to show it all the way out. I'm missing this part. I'm missing another red. Hate that line did that, but oh well. I'm missing another. Oh, hate that line did that. My gosh, like I never used a ruler before. And then last of all, this tree diagram just got, this ruler is the wacky one. Okay, there they are. That's actually all of the arrangements of red, blues, and greens. 2 reds, 1 blue, and 3 greens. So I guess maybe it wasn't that green sock. Oh, that means there's more here, and there's 1 more there, and there's 1 more. Oh, this is going to get very cumbersome. 4, 5, 6, red, red, blue, green, green, green. Red, red, blue, green, green, green. Maybe we need to do tree diagrams just once to be like, yo, never again. Or sometimes again. There is a way that we can write them more simply. That should be popping up here in a little bit. Red, red, blue, green, green, green. Red, red, blue, green, green, green. Because we're replacing, right? So if we draw a red sock, we're going to put it back in the pile. There's still 2 reds, a blue, and 3 greens available. Red, 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 blue, green, green, green. Red, red, 2 red socks, 1 blue sock, 3 green socks. Okay, that is the way to represent all of the possible events. And if you count the ends of the tree branches of the tree diagram, that green got a little bit on the wrong side. There's 6, 12, 18, 24, 30, 36 total outcomes. By the counting principle, 6 times 6 total outcomes. Maybe we could make a list from that. And so making a list, it'd be red sock with red sock. Then it'd be red sock with the other red sock. Then it'd be red sock with a blue sock. Then it'd be red sock with a green sock. And so we start to make a long list of numbers. The tree diagram is going to be our way to represent it. Calculate the probability of randomly. Why are there 2 words? Of randomly choosing a blue sock and then a red sock. So that one, I'm going to use 3 different highlight colors because there are 3 different probability arrangements. Choosing a blue and then a red means I'm going to choose a blue first, blue sock. Okay, I reached in. Hey, I got a blue sock, yo! And then a red sock. Well, that could be this one or this one. Only those 2. That happens 3 times. No, 2 times. This branch goes to that red sock, or this branch goes to that red sock. So it turns into 2 out of 36. If you think about it, there's 1 blue sock option, and there are 2 red sock options. So 2 out of 36, that reduces down to 1 out of 18. That's actually not a number we need to know. This is the better number because it tells us how many outcomes, it tells us how many events. That's the better option. Okay, yellow. A red sock and then a sock that is not blue. So a red sock, which would be down this branch, and then not a blue one. So red, red, green, green, green. Or this one is red, 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 green, green, green. And if you count the number of branches that are here at the end that are that scenario, first a red and then not a blue, first a red, then not a blue. There's 1, 2, 3, skipped over the blue, 4, 5, 6, 7, 8, 9, 10. There are 10 outcomes out of 36 total where the first sock choice was red and the second sock choice was just not blue. If we want to consider them separately in terms of their probabilities, that would be 2 out of 6, because 1, 2, 3, 4, 5, 6. So there are 2 out of 6 choices, and we're going to multiply by the number of choices that are not blue. So 1, 2, 3, 4, 5. Out of 6 choices not being blue. There's your 10 out of 36 when you multiply the fraction. I left the last one not done, like ahead of time. So we're going to do the last probability situation here together. 2 socks, with the first sock being green. So probability of green and who cares? Okay, probability of green and who cares. Let's color that one pink in terms of highlighter. That would be green, who cares? And otherwise green, who cares? Otherwise green, who cares? That would be 6, 12, 18. 18 out of 36 total combinations available. But if you think about it, it would be 3 out of 6 for the first choice. And I mean, all of these choices are available. So 6 out of 6 available for the second choice. There's your 18, and there's your 36. Maybe some questions. Let me read for a minute here. No, I didn't write it that way. Did you see counting principle happening? Counting principle happens when you multiply the fractions of the probabilities. 1 and 2, 2 and 5, 3 and 6. Those are counting principle situations because of how many times something shows up. That has been page 797. Looking forward, we didn't quite get into a do not replace scenario. For those of you watching this during class, don't be shook. You still probably have more class time to do. This is just the end of this period when I'm recording it. Thank you for watching, commenting, liking, and subscribing. I'll see you in the next episode. Page 797. Have a good one.